Okay, the last case in section 4.3 dealing with a differential equation uh, with constant coefficients, a linear differential equation with constant coefficients. The two possibilities that we looked at before was that from the auxiliary equation, if those roots are distinct, that was case number one, or those roots for m could be the same or repeated roots. We looked at that. And then thirdly, the possibility that the roots could be imaginary or complex conjugates. And so here we want to be able to write the solution that is universally accepted. Okay? So you would think where we have m sub 1 and m sub 2 are complex, if they're complex, then we can write m sub 1 as alpha plus beta I, and then m sub 2 as alpha minus beta I, and then just write the solutions with respect to how those terms are written. I mean, that would be fine. But in a universal sense, the solutions here look like combinations of cosines and sines because they use Euler's formula to go in between two transcendental functions, this e to some imaginary unit being inscribed into combinations of cosines and sines. So the way you would think that we would write the solution is that y is equal to c sub 1 times e to the alpha plus beta I x, and then plus c sub 2 times e to the alpha minus beta I x. Euler's formula is useful here in that the formula says that you can go from e to the imaginary unit of some angle theta, and you can relate that to cosine theta plus I sine theta, and maybe in geometry class you prove that. So if that be the case, then we want to be able to write the solution for a complex conjugate for a differential equation with constant coefficients in terms of cosines and sines. And let me show you how that is done, and just look at how we get it, and listen. What I go over, it's possible that it could be a test question itself, because it is necessary that you know why we write answers in certain ways in this particular class. We do not take it for granted. We do not just accept what somebody is saying. You want to be able to see it for yourself, and then to be able to show using, in this case, the mathematical rigor, and it's not that rigorous, by the way, to show that what you're saying is indeed sound. So here's what we have. If m sub 1 is equal to alpha plus beta I, and m sub 2 is equal to alpha minus beta I, then y sub c is said to be c sub 1 times e to the alpha plus beta I, not beta x, excuse me, parentheses times x, plus c sub 2 times e to the alpha minus beta I times x. Now I'm going to simplify that, because notice that e to the alpha x would be common in both of these terms. So we can write this, just factor out that e to the alpha x, this is times brackets c sub 1 times e to the beta, let's write it like this, beta x I plus c sub 2 times e to the negative beta x times I. Now Euler's formula is important. You have Euler, Leonardo Euler, Augustin Cauchy, and mathematicians argue about this, but definitely Euler, Cauchy, Isaac Newton would probably be in the top three in terms of the mathematical minds that have shaped our Western thought, our Western civilization. From their studies, and some of it was compiling what was known and had before them into certain manuscripts and books, but was published and given to the world. And so a lot of what you do in calculus in terms of proving, using epsilon and delta comes by way of Auguste Cauchy. And then a lot of what you do in terms of algebra, geometry, and trigonometry comes to us by way of Euler. And then the study of limits and calculus, partly so from Isaac Newton. There were others, his instructor, Barrow, and then another gentleman in Germany, Leibniz, who really studied the same concept. But I think those three in the top tier of our study of mathematics even today. Whether it's mathematics, physics, it's all grouped into the same spectrum. So Euler's formula says this. So from Euler, we have e to the I theta is equal to cosine theta plus I sine theta. And using that, I want to be able to write this equation using Euler's formula. In particular, especially the parts that are e to the some term times I. That's the part that we're concerned with. And so we say that this implies then that y sub c is that e to the alpha x, we leave him alone, c sub 1, and say parentheses, this e to the beta x I is going to be cosine beta x plus sine beta x, is an I in front of that one, by the way, from Euler, plus I sine beta x. So that takes into consideration or into account the c sub 1. Now plus c sub 2, parentheses, cosine negative beta x plus I sine of negative beta x. Okay, so you close up the parentheses, close up the bracket. Now, recall that cosine of negative x is equal to cosine x, and sine of negative x is equal to negative sine x. So using those two identities from trigonometry, we can represent this cosine negative beta x. That's just going to be cosine beta x. And then this sine negative beta x is going to be negative I sine beta x. So let's write that. So this is y sub c. The complementary solution is e to the alpha x times the brackets c sub 1 times parentheses cosine beta x plus I sine beta x, close that parentheses, and then it's plus c sub 2 parentheses cosine beta x minus I sine beta x. All right. Now I'm going to do some grouping. I'm going to group the cosines together, then I'm going to group the sines together. So y sub c, I will not skip a step. So I'm just going to run the c sub 1 through the parentheses, then run the c sub 2 through that set of parentheses. Then after that, I'm going to group. So this is c sub 1 times cosine bx plus c sub 1 times I sine beta x, excuse me, not, I am using beta and alpha, I'm sorry. So it's beta. Then this is plus c sub 2 times cosine beta x minus c sub 2 times I sine beta x. Now let's get the cosines together. So y sub c is equal to e to the alpha x. When I get the cosines together, notice here that I have c sub 1 plus c sub 2 all times cosine beta x. And then plus parentheses c sub 1I minus c sub 2I times sine of beta x. Is it kind of cool outside? It's kind of windy. Kind of cool. Okay. If that be the case, if you could just indulge with me, and I want to put some hats on C1 and C2 because it's windy, and even I have a bald spot there. So I'm going to put a hat. Can I put a hat there? Just put a hat. Just because it's windy. That's all. Just putting a hat on these guys, and I'll show you why in this next step. I should have called those guys something else initially. I was thinking that, and then I forgot. So here, a constant plus a constant is a constant, right? A constant plus a constant is a constant. So c sub 1 hat plus c sub 2 hat is equal to a constant. We'll just make it simple for us. And then this is a constant. This c sub 1 hat I minus c sub 2 hat I is also a constant because I is equal to what? The square root of -1, right? That's I. That's the imaginary unit. So it's a number. Right? It's imaginary, but it's a number. So this c sub 1 hat plus c sub 2 hat is a constant, and then this second term over here is a constant. So I'm going to represent them with a constant that we already know. We'll just make it out on ourselves. So let c sub 1 equal to c sub 1 hat plus c sub 2 hat. And let c sub 2 equal to c sub 1 hat I minus c sub 2 hat I. So the solution is y sub c is equal to e to the alpha x times bracket c sub 1 times cosine beta x plus c sub 2 c sub 2 sine beta x. for complex roots of m where that came from a m squared plus bm plus c equal to 0. So the way that you're going to write your solution, if you have those complex roots, is by that form there. You see why I put hats on C1 and C2, because I really want to use C1 and C2 at the end, and I didn't want to confuse you by saying let C1 equal to C1 plus C2. You know, just say, it's kind of funny. Letters are not humans. They just exist at our own discretion. So if I call them something else, it's okay. It's okay. You know. Now going through this, and you go through it, please do, because just this question right here just may be on the test. And so going through that, you appreciate that form and you understand it, so that when you write the solution for the complex conjugate, there's no question of why there is a cosine and a sine there. Okay. So now you got to remember this. Ooh. Well, don't remember that, but so remember, from m equals to alpha plus or minus beta I, we have y equal to e alpha x times c1 cosine beta x plus c sub 2 sine beta x. Let's look at a problem where we have to make use of this. All right, this is number 11 from the textbook. Now, you know that we can go right to the auxiliary equation, which is m squared minus 4m plus 5 equal to 0. Unfortunately, we just cannot factor, so we have to use the quadratic formula. So it's negative b, well, b is negative 4, so this is 4 plus or minus the square root of b squared, 16 minus 4 times a times c. It's just 1 times 4 times 1 times 5, all over 2 times a, and a is equal to 1. So we have 4 plus or minus the square root of negative 4 divided by 2. So we get 2 plus or minus this is 2i, divided by a 2 there. I already divided the 4 by 2. So this is m is equal to 2 plus or minus I. All we need is that alpha is equal to 2 and beta is equal to 1. So we can write the solution in that form. So the complementary solution is e to the alpha x, 2x, times c sub 1 cosine beta x plus c sub 2 sine beta x. Right? Use bracket or parentheses, it doesn't matter. Any questions there? All right. Number 13. Alrighty. So the auxiliary equation (3m squared plus 2m plus 1 equals to 0. Try to factor that. You won't be able to get combinations of 3 and 1 positive to give you a positive 2. So we use the quadratic formula. So m is equal to negative b, or negative 2, plus or minus the square root of that 2 squared is 4, minus 4 times a, which is 3, times c, which is 1, divided by 2 times a, which is 3. So we get negative 2 plus or minus the square root of 4 minus 12, negative 8, all over 6. So m is equal to negative 2 plus or minus, this becomes 2i times the square root of 2, all over 6. So we get negative 1/3 plus or minus I times the square root of 2, all over 3. We'll just pull out two things that we need from there. We just need alpha and beta. So alpha is negative 1/3, and beta is the square root of 2 over 3. So we can write the answer. So y sub c is e times alpha times x, negative 1/3 times x, times c sub 1 times cosine beta, the square root of 2 over 3 times x, plus c sub 2 times sine, the square root of 2 over 3 times x. Okay. Everybody fine with that? Okay. All right. Well, let's look at section 4.4. Let me finish this day with section 4.4. Section 4.4 will take the same concept one step further. And that is, notice in 4.3, we are solving the homogeneous linear differential equation with constant coefficients. What does homogeneous mean? The differential equation is equal to 0, right? So 4.4 will seek to solve a linear non-homogeneous differential equation of order n with constant coefficients. So, and the approach that they use is called the superposition approach.